Hi, I'm Hugo Lefebvre, second-year PhD student at the University of Manchester. I'm going to talk about FlexOS, or how to easily specialize OS safety properties. In the first third of this talk, I will provide a summary of FlexOS. Then, I will elaborate on future work questions that I am envisioning. The design of FlexOS was presented at HotOS 21, and we have a full paper at ASPLOS 22, so I will not focus too much on it. If we take a look at current OS designs, it is quite clear that security or isolation strategies are typically fixed at design time. Taking the example of a typical monolithic operating system, such as Linux, there is the user kernel separation and the process abstraction using the page table, and this is quite set in stone. Similar observations can be made for other OS designs, such as microkernels or single address space operating systems. And the result of this is a view of the operating system that does not work very well with modern specialization or hardware heterogeneity trends. What, for example, if you want to remove the user kernel separation in Linux? You might want to do that for performance reasons, and this is going to be very costly. What if you want to use cherry capabilities or memory protection keys instead of the page table for safety? Same issue. So what we wanted to propose with FlexOS is a different approach where we decouple security or isolation mechanisms from the design of the OS in the first place. The goal was to be able to achieve a range of security/performance trade-offs instead of a single point in the design space. We aimed to support a range of isolation mechanisms, hardware and software, and granularities. In essence, we wanted to specialize the OS for security for given use cases. Now, let me give you a 10,000 feet overview of how FlexOS works. In practice, users would come with a simple configuration file describing the system that they want to build, selecting an application, libraries, safety mechanisms, and boundaries. Following this, the toolchain would select an isolation backend that is going to provide safety primitives for the system. Isolation backends can leverage software as well as hardware-based technologies, such as memory protection keys or virtual machines. Then, the toolchain automatically rewrites the application and libraries to match requested properties. Finally, with this backend and rewritten libraries, the toolchain generates an appropriate image. The first piece of future works that I am going to mention regards isolation backends and underlying technologies labeled with 2 on this slide. The second one regards porting, or how the libraries shown in 3 are produced. In its current state, our prototype of FlexOS supports 2 isolation technologies. The first one is Intel MPK. It allows for fast domain transitions using highly available hardware, but the maximum number of compartments is limited for architectural reasons. The security guarantees are also limited since we don't have execution protection. And finally, the granularity of shared data is limited to a page. The second mechanism that our prototype supports is VM-based isolation. Compared to MPK, it offers significantly higher security guarantees and doesn't require hardware support. But it is rather slow, still limits the number of compartments that we can achieve for performance reasons, and also only supports coarse-grained sharing. These 2 isolation backends are quite a nice illustration of FlexOS's spectrum, being as diverse as intra-address space isolation and different VMs. On the other hand, they still have some limitations that ultimately limit the design space that we can achieve with FlexOS. For example, the number of compartments or the granularity that we can achieve. So now I'm asking, how can we better leverage FlexOS's potential in terms of performance and safety? One approach that we are exploring here is to support Cherry hardware capabilities. Cherry capabilities are an ISA extension that offers architectural support for capabilities. They are fast, even if it still has to be demonstrated on a real-world board, allow for an unlimited number of compartments in theory, and fine-grained shared data. But on the other hand, they require even more porting and hardware support that is not widely available yet. The really nice thing about Cherry is that it really gives you the ability to have a huge number of compartments with this high level of guarantees and fine-grained control over shared data. Ultimately, this allows us to explore highly partitioned scenarios, something that we couldn't do for architectural or performance reasons previously. It also allows us to validate our compartmentalization API with a new backend that has a particular properties. And finally, that allows us to perform a head-to-head comparison of Cherry with other mechanisms. The second area that we envision to improve on is porting. Let me give you a quick summary of how this works. So in practice, you would have an external developer producing libraries that we like to use in the context of FlexOS. It could very well be Nginx or OpenSSL. An expert is then going to port the library to a pool of libraries usable for FlexOS. In the case of complex libraries, we saw this cost going up to 5 days. Finally, the build system will use these libraries to automatically produce FlexOS images with varying safety profiles and mechanisms. The good point of this approach is that we typically get excellent performance since the expert knows very well the code base in its critical parts. The first downside is its cost. It is not always easy to find an expert. The second one is soundness. Since we rely on a human to port, human error is possible. In the case of FlexOS, this would not result in a safety issue, but in a crash, which is not wishable in production. Finally, every update has to be ported, which makes maintenance hard. So in practice, we observe that expert work enables high performance, but ultimately hurts the real-world impact of FlexOS. So the question that we ask is, can we achieve the same level of performance and safety without manual porting? Now, if we take a look at previous work, we realize that most of it has the same problem as us. A small number, though, of papers proposed fully automated compartmentalization. So typically here, you would have, once again, the developer producing libraries, except in this case, the toolchain takes care of porting and building without the help of an expert. This is nice because it makes compartmentalization highly usable, but it has a performance cost. And that is because of the limitations of static analysis. The tool has to be conservative, and legacy software that wasn't meant for compartmentalization. You have anti-patterns that cannot easily be automatically addressed. So, in fact, this is not really compatible with our goals in FlexOS. And what we'd like to know is, can we get the best of both worlds, the expert and the automation? So what we are proposing here is to have, again, the situation where libraries can be used automatically by the toolchain to produce images. Only here, the tool is going to produce, as part of this image generation, feedback that will allow an expert to produce annotation to the source code to increase the quality of the compartmentalization. Ideally, these annotations would be easy to maintain or even upstreamable. So here, annotations don't serve as a compartment boundary. They only really serve as hints to the tool. The goal is really to use the expert's help, if available, where it has the most added value over automation. The goal is really to achieve compartmentalization that is highly usable, that is sound, and produces excellent performance. So as a summary, in this talk, we quickly motivated the need for more isolation flexibility, whether it is for specialization purposes, heterogeneity problems, or even because your community is broke. FlexOS, our work from HotOS 21 and ASPOS 22, aims to address these issues. In this presentation, I elaborated on some future work direction that we envision. The first one was to support Cherry for increased design space and automated porting for the practical impact of FlexOS. Of course, we are also elaborating on use cases explored by FlexOS and seeing what we can enable in the real world. And I'm now happy to take questions.